Hi, welcome back. We're going to be continuing today with the next topic in the book, which are called nullclines. And nullclines just give you um, another way to fill in global information when you have a nonlinear system. We saw last time how to linearize around each equilibrium point to get a feel for what everything looks like. But the truth is that away from the equilibrium points, you have no idea what things look like. It's a lot like if you graph a function, if you know what things look like near the roots, that just tells you what it looks like near the points where it crosses the x-axis. But it could do anything anywhere else. It could wiggle and then come back down, go back up, etc. So, you might think if the function crosses the x-axis here and is going up and here and is going down, it probably goes up and then down, but it might do all kinds of stuff before it comes back down. Same thing is true with a phase portrait for a system of differential equations. Knowing what's happening near the equilibrium points can possibly help you fill in the entire picture, but sometimes bizarre things can happen and we need some other more sophisticated techniques. So that's exactly what we're going to do here. This technique isn't particularly sophisticated. In fact, we'll see it's probably a lot easier than the work we did last time. So let's just jump right into it. Let me share my screen. A minute here. And this happened last time. What do I do? Just give me a sec to get this technology working. Still not seeing anything here, are we? Let's try this again. Nope, still not seeing anything. Oh, there we go. There we go. There we go. There we go. All right, great. Sorry. All right, so here we go. Here we have another nonlinear system. This is actually quite similar to one of the systems we saw last time. So the first step is to solve for the equilibrium points. And when you do that, remember you're setting this equation, the top equation equal to 0, and the bottom equation equal to 0, and then simultaneously solving those, finding the values of x and y that simultaneously satisfy both those equations. And that tells you where the equilibrium points are. And the trick with nullclines is to do half that work. Okay, just solve the first equation, set that first equation equal to 0, just solve for y in terms of x, and that gives you certain global information. Then look at the second equation, that gives you certain global information. And then when we get to the equilibrium points, we're kind of putting those together to give you local information. So I'll try to explain what I mean by all that. So let's take this one at a time. Let's just first look at this top equation, this one here, okay? We've got x times 1 minus x minus xy equals 0, all right? Well, right away I can see I can pull out a 0 unless x is 0, right? You can divide by 0 unless x is 0. So this tells me either x equals 0 or we have 1 minus x, I'm dividing everything by x now, minus y equals 0, right? And that tells us that y equals 1 minus x. All right, now what did that tell us? Let's look at that top equation. This top equation says when this equals 0, we're saying dx dt equals 0. Right, so that's saying that the dx dt component of the vectors in the phase plane is 0. All right, now if the dx dt component, now that's the horizontal component. If the horizontal component of a vector is 0, that means the vector has to be vertical. Okay, so everywhere along the line x equals 0 and the line y equals 1 minus x, I know all of the vectors along those lines are vertical because along those lines, the dx dt component of the vectors are vertical. So if I'm just filling in the phase plane here, let's see what this looks like. Here's the phase plane. Oops, wrong tool. Here's the phase plane. Okay, x equals 0. That's just the y-axis. Right? This is the y-axis. So I'm saying everywhere along the y-axis, these vectors are all vertical. So I don't know if they point up or they point down, but they're all vertical. So I'm just going to fill in little vertical vectors, and I'm going to wait to put the arrowheads on these vectors. Maybe I should switch colors, sorry. I'll fill in these vectors, and I'll wait to put the arrowheads on these vectors until until I know whether or not they point up or down. But for now, I know that they're vertical. Okay, and then there's also the line y equals 1 minus x. So that's a line of slope -1, and it has a y-intercept of 1. So up here, whoops, having technology issues. Up here at y-intercept of 1, that's 1 there. I know all the vectors along that line are also vertical because those are also places where dx dt equals 0. So that means I can start drawing those vectors and they'll all be just these vertical. Right now they look like just vertical tick marks. I don't know if they point up or they point down. If we want to know if they point up or they point down, we can just test one of them and it'll tell us lots of information. But let's hold off on that for a second. We also have this second equation. Now, the second equation are the places where the dy dt component of all of the vectors in the phase plane is 0. The dy dt component is the vertical component. So the vertical component of a vector is 0. It means the vector is horizontal. So if I set this equation equal to 0, what do we have? We got, let's just do it. We've got 2y times 1 minus y over 2 minus 3xy equals 0. So again, that means either y equals 0, or I can divide both sides by y, and I get 2 times 1 minus y over 2 minus 3x equals 0. Let's distribute the 2. That gives us 2 minus y minus 3x equals 0. And that gives us y equals 2 minus 3x. Okay, so that's a line of y-intercept 2 and slope -3. Right, so I'm going to go up here to this picture again, and I have to draw. Let's extend this axis up here, way up here at 2. I'm going to draw a line of slope -3. So that's much steeper negative slope. It's going to intersect the other line at some point. And everywhere along that line, I know the vectors are horizontal. So I can just fill in these horizontal tick marks. Okay, and also, that was this one here, also everywhere along the line y equals 0, which is the x-axis, all the vectors are horizontal. So let's fill those in. Okay, now there are a couple of special points here that we're seeing where the nullclines intersect. So let's look at those real quick. We've got one point right here at the origin where the x nullcline and the y nullcline intersect. The dx dt equals 0 nullcline and the dy dt equals 0 nullcline intersect. There's a point way up here at x equals 2 where the two nullclines intersect because the y-axis is a dx dt nullcline, and the line, that slanted line up there, is a dy dt nullcline. Then there's this point right here, we already said, is a place where both equals 0. And this point over here is another place where both of them equal 0. This point is not a place where they both equal 0. That's a place where the dx/dt nullcline, one of the dx/dt nullclines intersects the other dx/dt nullcline. It's not a place where the dx/dt nullcline intersects the dy/dt nullcline. So those black points I indicated are just the places where the two different nullclines intersect. Okay, so this black point, for example, that's a place where dx/dt equals 0, because we're on the dx/dt nullcline, and it's a place where dy/dt equals 0, because we're on the dy/dt nullcline. And if we know they're both 0, that gets us back to the stuff we were doing last time. It means that's an equilibrium point. So these big dark blobs that I've just indicated to you, those are the equilibrium points. You could just see them in the picture. The equilibrium points are the places where both equations are simultaneously 0. And so those are exactly the intersections between those two nullclines. All right, get rid of that. All right, so we can go back and do everything we did last time and do the equilibrium point analysis here. Let's do a little bit more. Let's think about just the logic of what's going on here a little bit more, okay? Let's focus on this region of this nullcline. Let's see, let me get another pen here. Just gonna look at this nullcline right here and this region between those two equilibrium points of this nullcline. This was one of the dy/dt nullclines, this part of it, and this part of it right here. Now remember, along that nullcline, I already know dy/dt equals 0. Okay. Now, let's just think about what's happening there. If dx/dt is positive, that tells me that the vectors along that line, well, I already know dy/dt is 0, so they're horizontal. And if dx/dt is positive, then they point to the right. And if dx/dt is negative, they point to the left. So, sorry, I'm probably turned around. I just realized in the video. If dx/dt is positive, they point to the right. And if dx/dt is negative, they point to the left. Okay, so we can just check for those points. It might help first to figure out what the coordinates of that point are. So that's the place where we have both this equation and this equation. So we can solve by setting those two equations equal to each other. So we have 1 minus x equals 2 minus 3x. So let's see, add 3x to both sides, gives us 2x on the left, and we subtract 1 from both sides, gives us 1 on the right. So x equals 1/2. And we know, again, y equals 1 minus x. So if x equals 1/2, we get 1 minus 1/2, which is 1/2. So that point up there is the point 1/2, comma 1/2. All right, now, if I'm on that line, let's pick a point on this line. Let's look at what happens when x equals 1/4. If x equals 1/4, let's look at this equation right here. Or sorry, let's look at this, go back all the way back to this equation right here. Okay. Oops. Well, I'll tell you what, I picked one that's too hard. Well, yeah, let's keep going with this. Sorry. I had a temporary brain freeze here. Let's just keep analyzing what's happening in this inside this green region here. I just want to figure out if on that line dx dt is positive or negative. Okay, so I want a point on this line. Let's just pick a point. If the equilibrium point is a place where x is a half, then somewhere along this line there's a place where x equals 1/4. Okay, now I want to be on that line, and that line has this equation over here. So if x is 1/4, that tells me y equals 2 minus 3/4, which is 1 1/4 or 5/4. Okay, so for instance, so that means there's a point on that line where x is 1/4 and y is 5/4. Right? And now I just want to check, is dy dt positive or negative? Well, on that line, sorry, dy dt is 0, right? That's how we found that line, is we checked dy dt equals 0. So what I want to check actually is what is dx dt on that line. So I'm going to plug in those values up here. I'll plug in 1/4 times 1 minus 1/4 minus 1/4 times 5/4. And all I care about here is if it's positive or negative. But let's keep going there. That's the first term is 1/4 times 3/4 is 3/16, and I'm subtracting from that 5/16. I get negative 2/16, which is certainly less than 0. And what that tells me is that those vectors just in that region are negative. They have a negative dx dt component, which means they have to point to the left. To the left. Okay. Now, if I know that vector points to the left, then I also know this vector has to point to the left. And let's talk about why in this one as well. In fact, along the nullcline between the two equilibrium points, I know the vectors point to the left. Okay. And the reason is, let's say they pointed to the left, pointed to the left, pointed to the left, and then they flipped, and then they're pointing to the right, right? Well, if they point to the left, they're negative. And then if they point to the right, they're positive. If you're going to transition from negative to positive, right, then at some point, that horizontal component has to be 0. But we're on the line where the vertical component is also 0. So if error flips from left to right, then that's a place where both the horizontal and the vertical components are 0, which means I'd see an equilibrium point there. But between these two equilibrium points in this green region, I don't see any equilibrium points, so it can't flip. So that kind of logic is super important, right? Once you test one vector and you don't pass through an equilibrium point, then all the other vectors have to point in the same direction. Okay, same logic goes down in this region over here. In this region over here, I know all the vectors are vertical between those two equilibrium points. And that tells me if any of them point up, then they all point up. And if any of them point down, just between those two equilibrium points, then they all point down. And then same logic down here as we keep going all the way down to the bottom right. If any of those vectors point up, then they all point up, and vice versa. Okay, and so we can keep this kind of logic going all the way through the diagram and really start to fill in the whole diagram. Okay, I want to do a little bit more. Let's now do the equilibrium point analysis. We already found out that one of the equilibrium points is right here. It's at 1/2, 1/2. We know there's an equilibrium point here at 0, 0. And we know there's an equilibrium point here at 0, 2. And we know there's an equilibrium point here. And that was, I believe, let's find out what that is. That's a place where I'm on the dx dt nullcline and y equals 0. So that's a place here where y equals 0. So that tells me x equals 1. X equals 1 right there. Okay, so my equilibrium points, just looking at the picture, I've got 1, 0. That's that last one I found. We've got 1/2, 1/2. We've got 0, comma 2, and 0, comma 0. So let's do the linearization from last time. We'll try to do this relatively quickly, and then we'll combine that with all this Nullcline information, and that'll let us fill in a really good picture, and I'll make the picture much bigger so we can really see what's going on here. And I hope I haven't lost any here, okay? So let's see, I need to copy this down. We've got x times 1 minus x times minus xy, x times 1 minus x minus xy. That's the first equation. And the second equation is 2y times 1 minus y over 2. 2y times 1 minus y over 2 minus 3xy. Okay, this was dx dt. This is dy dt. For the equilibrium point analysis, we're going to have to take the partial of these. For taking the partials, I think it's easiest to actually multiply them out. So let's go ahead and do that. This equals x minus x squared minus xy. This equals 2y minus y squared minus 3xy. So the matrix we get are, I got to take the partials of the first equation with respect to x and y. Partial with respect to x is 1 minus 2x minus y. Partial of the second equation with respect, partial of the first equation with respect to y, which is minus x. Partial of the second equation with respect to x is just minus 3y. And the partial of the second equation with respect to y is 2 minus 2y minus 3x. All right, at 0, 0, we have the matrix 1, 0, 0, 2. Okay, that's a source. Okay, and that tells us a lot of information already. You know, I can go back up here. Boy, that tells me a huge amount of information. If that's a source, everything's pointing away from it. So I know this vector points up, this vector points down, which means all these vectors point down, and all these vectors point up until I hit the next equilibrium point. Okay, and that means this one right here is really key. It points up, which means this one also points up, and this one also points up, and this one also points up, and this one also points up until I hit that equilibrium point. So boy, just knowing it's a source let me fill in a lot of this picture. And I'm not done. Since it's a source, I know horizontally, this goes to the left and this goes to the right, which means to the left of the origin, they all go to the left. And they all go to the right of the origin. And this one here I'm drawing right now, if you can see that, is also in the other one, which means all the ones on that one have to go to the right. As long as you don't hit it, so you walk along the Nullclines, the sense of the vectors, left, right, up, down, doesn't change until you hit an equilibrium point. So leaving the origin going to the right, I know the vectors point to the right. If I then walk along the other Nullcline, when I hit it, they still walk to the right until I hit that equilibrium point. Okay, so I just knowing what's happening at 0, 0, let me fill in a tremendous amount of this picture. Okay. Let's keep going here. Let's see, let's just now look at the picture, see what else we need to fill in. Let's look at what's happening down there in the bottom right at 1, 0. Still don't have a lot of information there. So at 1, 0, at 1, 0, now I have, let's see, 1 minus 2 times 1 minus 0 is negative 1. Negative 1, 0, and 2 minus 0 minus 3, well, 2 minus 3 is also negative 1. All right, that to me looks like another source. It's got actually a repeated equilibrium value. sorry, repeated, what am I saying? A repeated eigenvalue of -1. Now remember the picture with repeated eigenvalues, either everything's a source, sorry, either every vector lies on an eigenvector, every vector is an eigenvector, right? So that picture would look like this. The local picture, right around that equilibrium point. Or there's just a line of eigenvectors, and everything else moves along one of these S-curves. But you know what? Right now, it doesn't matter. The point is it's a source. Everything somehow moves away from that equilibrium point. And I'm sorry. Please erase the last minute of this video. If I was better at video editing, I would do that. The eigenvalue is -1, which means -1 is a sink. So again, if there's a sink, then either everything is an eigenvector and goes directly toward the origin, or everything, or there's a line of eigenvectors and things go toward the origin, but maybe along more complicated curves. Doesn't really matter. We can fill in the picture going back up here, right there at 1, 0. I know that this has to go toward the origin. If it's horizontal, it's got to move toward the origin. And that means this one goes toward the origin, okay, etc. Right? And let's see, the red ones, it's not clear what's going on with the red ones, but it's got to be a source. I mean, it's a sink. So a sink, we know this is vertical down here, so it can't point down since that equilibrium point is a sink, so it's got to point up. It doesn't point directly toward the equilibrium point, but it certainly can't point away from it. And same thing over here, this one has to point down. Okay, which means this one down here points up, etc. Okay, so now just knowing a little bit about the equilibrium points, just knowing 2 equilibrium points, that the origin is a source and that 1, 0 is a sink, we've really been able to fill in most of the picture here. Let's do one more, 2, 0. Let's do 2, 0. At, sorry, 0, 2, 0, comma 2. 0, comma 2, we have the matrix, let's see, 1 minus 0 minus 2 is -1. And 0, 0, comma 2, so that's -6. And 2 minus 2 times 2 is -2. Okay, again, that has negative eigenvalues, -1 and -2, because it's a triangular matrix. You can confirm that for yourself, but it's pretty quickly. So that tells me that I have a sink here as well, which means everything points toward that last equilibrium point. Okay, so let's put it all together. Okay, so let's just draw this picture much bigger. I have a line of slope 1 through 1. Sorry, slope -1. A line of slope -3 through 2. That intersects at 1/2, comma 1/2. I have equilibrium points here at 1, 0, and up here at 0, 2, and one here at 0, 0. I've got an X nullcline and a Y nullcline, right? I'll keep going. The blue ones are the X nullcline, so that's right. The blue ones are the places where dy dt is 0. Everything's horizontal. So that's the steeper of the 2 diagonal ones. So that's this one here. And I know the origin was a source, right? So things move horizontally away. Okay, until I hit that equilibrium point on the right, which is a sink, so things move toward it. Okay. And also that diagonal one is another the other dy dt nullcline is the steeper of the two diagonals. Okay, so I have some information there. And kind of fill it in. And then when I hit that equilibrium point, the direction changes. That doesn't always happen, but in this case, it certainly does. When I hit this equilibrium point on top, the direction changes. Okay. The other lines in this picture are the other nullcline, where things are vertical. Okay, I've got, again, the origin is a source, so things will move away from the origin. I hit the equilibrium point up top here, and the direction changes. And along the other diagonal equilibrium point, things stay the same. I haven't hit any equilibrium points yet till I get to that one in the middle where it's going to flip. Then I hit that one at the bottom where it flips again. All right, now we can start answering more qualitative questions once we have this full picture. So with this full picture, I can start asking you questions like, suppose I have an initial condition that is, we'll do it in green, that is in this region here. Do you see this region? There's this triangle there, right in the center of the picture, just above and to the left of that central equilibrium point at 1/2, 1/2. So let's think about what happens to that point. If you look at the blue arrows next to it, they're pointing to the left. Okay, so that point is going to start getting pushed to the left, but then they run up against the red arrows, which push it up, which tells me that the fate of that point has to go up, and eventually it's going to get sucked into this equilibrium point here. So it's moving upward like that would be the trajectory of a point like that. Okay. Same thing down in this bottom right triangle. Those points will get sucked into this equilibrium point. They're kind of trapped in that triangular region. They can't get out of that triangular region because then they'd have to cross those nullclines with the arrows going the wrong way. Okay. Let's think about some other regions here. You know, down at the bottom right, things are just going to move away from the origin somehow. I don't know how. So bottom left. Points over here, they move away from the origin. Now, nullclines aren't trajectory lines. Okay, remember, two trajectories of a differential equation, two solution curves, another way to say it, can't cross. But you can cross a nullcline. You just have to cross it in the right direction. So if I cross that red nullcline, I have to do it so that the tangent vectors to that nullcline are vertical. Things have to be vertical there. Okay. And eventually, if I ever cross the other one, things would have to be horizontal. And then maybe I get sucked into this point. Okay, it's not clear what's happening there. It's a little bit hard to say. Another possibility is that we go up and we just go up and kind of get sucked that way. So again, we don't have that much global information. So it's very hard to say what's really happening here on that point. Oops. All right, let's look at a couple other points here. If I have a point, now there's this region kind of an interesting region down here. I wonder if I can zoom in. No, this program doesn't allow zooming. I'm going to use yellow here. There's a yellow curve here. We can't really see it. And we don't have the tools to find this curve right now. But the yellow curve is kind of interesting because it divides those regions into two different places. Up here in this upper left triangle, that's all those points are going to be pushed upward. They're going to cross the nullcline here, and then they're going to get sucked into this equilibrium point. And the points over here will get pushed to the right and get sucked into the other equilibrium point. Same thing over here. All these points are going to go down, and all these points here are going to go up, like that. Okay? And so really what you have is, especially in the positive quadrant, there's really two types of behavior. Everything's going to get sucked into this equilibrium point here or into this equilibrium point here. Depending on what side of this yellow line you're on, you'll get sucked into one side or the other. Right? So that really tells us a whole lot of qualitative information about this differential equation and about the behavior of various points on this differential equation. All right, we have a little bit more time here. Let's see how much time we have. I have no way of knowing how much time we have. So let's do one more quick example here. It's not so quick. We'll do one more example. I hope you're getting the sense from the very, very beginning that this is actually, it may seem much more complicated right now, but it's actually easier than what we did before. Before we set both equations equal to 0 and solved them simultaneously to get the equilibrium points and then did a whole bunch of calculus. That's all still there. You all still have to do all that. The only thing we're adding to that is to set each equation equal to 0 individually, not simultaneously. And then that gives you curves where the arrows are either horizontal or vertical. That's the takeaway from today. That's it. Set the dx dt equation equal to 0. That gives you a curve in the plane or a set of curves in the plane where the vectors are all vertical. If you set dy dt equals 0, that gives you a set of curves in the plane where the vectors are all horizontal. That's it. Okay. So let's do one more example where we see this kind of behavior here. So again, if I set dx dt equal to 0, I get the places where the vectors are vertical. So let's just do it. X times 1 minus xy equals 0. Either x equals 0, or I can divide everything by x and I get 1 minus x minus y equals 0. So y equals 1 minus x. Okay, that's identical to what we had before because that first equation is the exact same equation to what we had before. Right? So we have these, again, a line where everything's vertical and another line where everything's vertical. All right, let's do the other one. 2y times 1 minus y squared over 2. That looks a whole lot like we had before, except before we just had y over 2, not y squared over 2. Minus 3x squared y, before we just had 3xy, equals 0. So again, either y equals 0, or we can divide everything by y, and I'll distribute that 2. That gives us 2 minus y squared minus 3x squared equals 0. And that gives me 2 equals 3x squared plus y squared. That's much more interesting. That is an ellipse. And in fact, if I just divide everything by 2, we can see that ellipse much clearer. It's 1 equals, and I'm going to write it like this, x squared over 2/3 plus y squared over 2. There's a reason I'm doing it that way. If the denominators weren't there, I hope you would all recognize that as a circle of radius 1. Right? That's 1 equals just x squared plus y squared if there's no denominators. Adding those denominators just rescales things in the x direction and the y direction. If you take a circle and rescale it in the x direction and the y direction, it becomes an ellipse. Okay? I'm not going to stress too much about the shape of that ellipse. I'm just going to draw kind of a random ellipse in. The point is, we have this curve where dy dt equals 0, which means all the vectors are horizontal, and another curve, which is an ellipse, where all the vectors are horizontal as well, right? So the blue stuff means all the vectors are horizontal. The red stuff means all the vectors are vertical. So we can already start to draw the picture here. And we'll get the hang of this technology eventually. There we go. All right, so along x equals 0, dx dt is 0, so the vectors are vertical. So the red stuff's vertical when x equals 0. X equals 0 is the y-axis, so all the vectors are vertical on the y-axis. Vertical on the y-axis. That's what this equation is telling us, okay? Y equals 1 minus x, just like before. That's a line of slope -1 in y-intercept 1. And there, all the vectors are vertical as well, just like before. But now, well, let's see, let's keep going, let's keep going. Along y equals 0, all the vectors are horizontal, just like we had before. And immediately I see two equilibrium points where I am on both the red curve and the blue curve. There's one right here at the origin. Oops, I want that to be black. Right, that's where red intersects blue, and there's another one right here where red intersects blue. So now I know I have equilibrium points just where I had them before at 0, 0, and 1, 0. Okay, so if I'm keeping track of the equilibrium points, I got one at 0, 0, and one at 1, 0. But we also have this ellipse, right? Well, let's just think about the x-intercepts and the y-intercepts of the ellipse. So let's jerk graph. Let's be a little more careful with this. So if I set y equal to 0, I get the x-intercepts, right? If I set y equal to 0, I get the equation 3/2 equals x squared. If I set y equal to 0, I get 3/2 equals x squared. So x is plus or minus square root of 3/2. Okay, now 3/2 is bigger than 1. Square root of a number bigger than 1 is also bigger than 1. And I'm going through all that just to indicate that this curve, this ellipse, has an x-intercept bigger than 1 and less than -1. Okay. The y-intercept, to get the y-intercept, I do 1 equals y squared over 2, which means 2 equals y squared. So y is plus or minus √2. So that's up, let's see, extend this axis up, plus or minus √2. √2 is about 1.4. So I have things up here somewhere, down here somewhere. Let's sketch this ellipse now. Oh man, that's a terrible picture. Let's try that one more time. That's much better. I missed that bottom point, which is okay. All right, so on the y-axis, I'm at plus and minus √2. On the x-axis, that ellipse hits at plus and minus square root of 3/2, whatever it is. Doesn't matter what it is. The point is that's bigger than 1 and less than -1, which means I'm to the right of that equilibrium point, okay? And again, that's a place where dy dt equals 0, which means all the vectors are horizontal. All the vectors are horizontal. all along that ellipse. All right, so I'm already seeing a couple other equilibrium points. Now there's one down here at the bottom. There's an equilibrium point. There's one right over here. There's an equilibrium point. And let's see, there's going to be one up here. That's an equilibrium point as well. And one over here. Ooh, stop that. Technology is really giving me trouble today. One up here. So I'm seeing 1, 2, 3, 4, 5, 6 equilibrium points. Okay, so I have the intersection of a circle and a line with 2 lines. There's 2 red lines, and there's a blue circle or sorry, a blue ellipse and a blue line. And other than that, I know things are vertical here. And let's see, we can continue this up, and things are going to be vertical, vertical, vertical. And in here, they are horizontal, horizontal. Right, so the black dots are just the places where the red stuff intersects the blue stuff. They're not the places where blue intersects blue or red intersects red. Right, so for example, I do not have an equilibrium point. I do have an equilibrium point here, but I do not have one here. All right, to go further and to put arrows on these lines, I'd have to now either analyze the situation between 2 equilibrium points, or I could do the equilibrium point analysis at each point, and that would tell me a lot. My guess is at the origin, things look very, very similar to the before. Of course, we'd have to do the work to make sure of this, but I would guess the origin is still a source. And if my guess is correct, let's just go with that guess. Things probably move away from the origin. That means they go away from the origin, away from the origin. Once I hit this ellipse, I can now start moving on the ellipse. Things are moving leftward, and they continue moving leftward. See how much of this picture going in I can fill in? And now, let's see, going vertically, if that origin is a source, I'm going up, 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 just till I hit the equilibrium points, and down, 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 okay, 90% of the time, not always. You have to be careful. This is an important lesson. This is not always true. But if you had to guess on a test and you were pressed for time, then I think it's always a reasonable guess that when you hit the equilibrium point, the direction flips. It's not always true. It's a lot like saying if you have a root of a function and you know the function's positive here, it might be positive over here, but most of the time what's happening is the function just crossing the x-axis. So you usually flip from positive to negative when you hit a root. Okay, so again, I don't know this is always the case, so this is now really just a guess, but I would expect that the direction flips. So for instance, in the top left here, I would expect things now point down, okay? And here I would expect things point down. And here I would expect things point down. And here I would expect things point up. Those are the red things. And then the blue things, I'd expect things to flip. So here I would expect they now point to the left, 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 which means this will be left, 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 left. And down and left. Down here, I would expect right, right. So I would expect this is the picture. We could plot it with software to find out. We could do the equilibrium point analysis at each equilibrium point to find out. One more little blue mark, I would expect right, just right in that little tiny range. If you were to successfully confirm all of my guesses here, go through the equilibrium point analysis, then you'd be able to tell me what the fate of a point right here is. There's not a whole lot of choices. You can't go through the ellipse because then we'll be going opposite to the blue arrows, and the red arrows are pushing us up. So the blue arrows are pushing us leftward, and the red arrows are pushing us upward. And so you could tell the eventual fate of this point is to get sucked into that equilibrium point. Now let me make sure that you all understand and just give you a word of caution here. That trajectory, that solution curve that I just drew in, that green solution curve, is an asymptotic curve. Hopefully you all know at this point, as you approach an equilibrium point, the vectors get smaller and smaller and smaller and smaller and smaller, which means it takes infinite time to actually get to that equilibrium point. So I say you get sucked into that equilibrium point, but the rate at which you approach that equilibrium point goes to 0 as time goes to infinity. Right, now let's say that point were 1/2 comma 3/2, just to be concrete. 1/2 comma 3/2. You know that point's going to get sucked into here at 0 comma what was that, square root of 2. Remember that came from this equation. So 1/2 comma 3/2, if it's actually in that region, it looks like it is, goes to 0 comma root 2. So again, if I ask a question on an exam for you, what happens with an initial condition of x equals 1/2, y equals 3/2, the correct answer would be, well, x is 1/2, but x is going to get sucked into a place where x equals 0, which means the solution curve will look like this. It takes infinite time to get to 0. And so that's on the x-axis. And then on the y-axis, we're starting with y equals 3/2. And eventually, y gets closer and closer to square root of 2. Square root of 2 is bigger than 3/2. Shoot. It's not bigger than 3/2. That's not a good point. Let's pretend that's 1/2. Sorry. One half. So if y is 1/2, square root of 2 is bigger than 1/2. So it'll look like this. It's 2. All right, so that's the story with Nullclines. Again, I mean, this was a fairly complicated example. This is a very complicated example. But in practice, things are not that complicated. And I'll just review what's going on here again one more time, make sure everybody understands it, talk it through very, very quickly. We've got 2 equations, okay? If I set the first equation equal to 0, I get a solution curves where all of the vectors are vertical. If I set the second equation equal to 0, I get solution curves where all the vectors are horizontal. Where those 2 sets of curves intersect, I see my equilibrium points. Those are those black dots. And then you can do the equilibrium point analysis, the linearization around each equilibrium point to tell you what direction the vectors are headed near those points. And then just knowing that information around those points helps you fill in all of the vectors on all of the nullclines, whether or not they point up, down, left, or right. And then once you know that, you can start talking about the qualitative information about what do solutions look like with a given set of initial conditions. Okay? That's a tremendously powerful, right? We never got a computer out. All these calculations were done by hand. So there was some guesswork involved with this particular example, but those guesses are pretty easily confirmed. With a couple more minutes, you can do that linearization work around each equilibrium point. And the derivatives aren't hard. You're just taking the derivatives of polynomials and getting some 2x2 matrices, getting the characteristic polynomial, figuring out the eigenvalues and eigenvectors, mostly that you're going to look for sources and sinks, and those tell you the directions of vectors around those points. Okay, it's not quite as bad as it. I probably made it all look. Sorry if I confused you today. I will be happy to answer questions by office hours or by email. So please do ask me questions if you have them. Not a lot of students from this class tend to show up to my office hours. Again, my office hours this point going forward for the rest of the semester have shifted to Mondays and Wednesdays from 9 a.m. to 10:30. And I will, I've been pretty good about being on Zoom during those times. So feel free to join me and chime in and ask questions. And of course, I'll answer questions on the homework at the beginning of class next time. Okay, so I'm going to sign off now, and good luck on the web work problems. There's only 3 of those.